Thanks. So we were talking about the Feynman propagator last time, and we were doing it first for scalar fields. And so let me go back to that. Let's see exactly where, maybe I should remind. Remind us how things are. What we're talking about is the so delta F is the Green's function for this operator. Which would be m squared plus d0 squared minus grad squared and what we said last time was that this was in fact a four-dimensional integral d4 q over 2 pi to the fourth e to the I qx over q squared plus m squared minus I epsilon. Now, what I don't remember is exactly how far we got in that. Were you taking notes last time? Do you remember when we stopped, more or less?
So if you stop here, we had some IQ. We broke this guy up into this guy. And
that was it? We had just started there, basically?
Mm-hmm.
All right, well, maybe there's no point in trying to find the exact place because we might as well just start the derivation essentially from scratch. Let's let I of q vector be minus an integral minus infinity to plus infinity dq0 over 2 pi e to the minus I q0 x0 1 over q0 minus EQ minus I epsilon times Q0 minus EQ plus I epsilon. So, and this minus sign out in front is because the Q0 squared occurs with a minus sign in the denominator. And so if we want it with a plus sign, then we pull out an extra minus sign there. EQ is what we normally call Q0, namely Q vector squared plus m squared, the square root of that. This is an integral along the real axis from minus infinity to plus infinity along the Q0 axis, and we're taking, of course, the limit epsilon going to 0, and we can see that there are poles here at EQ minus I epsilon and at minus EQ plus I epsilon. And so if x0 is positive, then that's positive, and so then you want to do you want to add a ghost contour around the South Pole, and you pick up the pole at EQ minus I epsilon, and so this gives you then, first of all, the overall minus sign, then e to the minus I, Q0 then is EQ X0, and Q0 is this one, so we pick up minus 2 EQ here, and this is if X0 greater than 0. On the other hand, there's an overall minus sign because we're going around clockwise. The 2 pi cancels and there's an I. So plus and then an I. If on the other hand X0 is less than 0, then what you do is you go around, you add a ghost contour like this, and you pick up the pole at minus EQ, and so this is then e to the I EQ X0. Then there's an overall minus sign, and what we have once again is minus 2 EQ, and so the answer then is that if we multiply through by minus I, it's minus I of Q is Q vector is 1 over 2 EQ theta of X0 e to the minus I EQ X0 plus theta of minus X0 e to the I EQ X0. These notes are all online. And so let's just see if I've got the sign right. We have a minus I minus I well, I think I'm off by a sign here, so let me just check this one again. What we're supposed to get is this thing is then 2 pi. Okay, we're picking up this one.
Did you disregard the minus sign that's out front of everything in your integral?
I just regarded something, I
Yeah.
think. So let's see, if X0 is positive, we do this. So then, because we're going backwards, we cancel this minus sign. We're picking up the pole at EQ. So that's 2 EQ, so it's a plus sign there. And then, in this case, when we do it this way, we keep that minus sign, but on the other hand, we have this one, and I forgot the overall I. And so in both cases, we have an I there, and we bring it over to the other side, we get a minus sign, 1 over 2 EQ, and then there's just the phase changes. Okay, so that's the awesome. So that's the key integral in this. The rest of the thing is pretty much simple. Now, so df is equal to this. There is, we just did the q0 integral. And so what we've got then is that df of x is or to put it, all right, for some reason I'm going to multiply by minus I. Minus I df then will give us an overall minus sign there. And maybe I shouldn't do so many things at once. Our delta sub f is just the simple integral, so let's just continue that way. One of the terms is this, and so this is I of q vector integrated dqq over 2 pi q e to the I qx. So that's what delta f is, and then I of q is, okay, if we multiply both sides by I, we get an I over here. So we get an integral dq over 2 pi q e to the I q dot x, and we have 2eq, and then we have theta of x0 e to the minus I eq x0 plus theta of minus x0 e to the I eq x0. And this term here, the first one then, is, oh, I forgot an overall I. Okay. So there's an overall I, and apart from that, this is delta plus of x. So this is I theta of x0 delta plus of x. And now what we've got is theta of minus x0 the IQ x0, and this is, we can flip q to minus q because q vector only occurs quadratically, and so this is equal to plus I theta of minus x0 delta plus of minus x. And so now, if we multiply through by minus I, we get minus I delta f of x is theta of x0 delta plus of x plus theta of minus x0 delta plus of minus x, x being the 4 vectors. Okay. So this is, in a sense, this is one way of thinking about the Feynman propagator, but we haven't yet fully connected it with physics yet, and so to do that we recall the expansions. If we're talking about a scalar field, then we have phi plus of x is dqp over the square root of 2 pi cubed 2p0 e to the I px and a of p and phi minus the negative frequency part is same thing, e to the minus I px. I'm talking about a real field, so we just have an A dagger there. And then, if we consider the commutator of phi plus of x with phi minus of y, we get something, I'll put a minus sign for commutator. What we get is an integral d cubed p, d cubed q, 2 pi cubed, square root of 2q0, 2p0, and then e to the I, px minus I, qy, and then a commutator, a of p, a dagger of q. This gives you a delta function, and so this just collapses into an integral d cubed p, 2 pi cubed, 2p0, e to the I px minus y, and this is what we call delta plus of x minus y. And so now by the way, parenthetically, so this is really a parenthetical remark here, delta plus for space-like, for x squared greater than 0, delta plus is m over 4 pi squared r k1 of mr, where this is a Hankel function, and r is the square root of x squared assumed positive. And so okay, so for scalar fields, the time-ordered product phi of x, phi of y, of course, is theta of x0 minus y0, phi of x, phi of y, plus theta y0 minus x0, phi of y, phi of x. And what we're going to do now is consider this, the mean value of this time-ordered product in the vacuum state. And so this is theta x0 minus y0. Well, maybe I'll put the vacuum over here. And this is then phi of x, phi of y, plus theta y0 minus x0, phi of y, phi of x, vacuum. Okay, now there are a series of about 3 tricks, each of them very, very simple. If we have a phi y here, the phi plus annihilates the vacuum on the right, so we can drop it, and so we only get phi minus there. On the other hand, phi of x, the only one that doesn't annihilate the vacuum here, is the positive frequency part. Over here, similarly, we get a minus and a plus. Okay. Next, we know that phi plus annihilates the vacuum on the right and phi minus annihilates the vacuum on the left, so we can turn this thing into a commutator at no cost because the opposite order vanishes. We can do the same thing here. But now we know this thing is delta plus, so this is theta of x0 minus y0 delta plus of x minus y. That's this term. And then this one is plus theta of y0 minus x0. And this is delta plus of y minus x. Okay, well that's it. That is what we call minus I delta f of x minus y, and this is the Feynman propagator. So the Feynman propagator for scalar fields is the mean value in the vacuum of the time-ordered product, and it is then minus I times the Green's function that we were talking about over here, and it's the sum of two delta pluses. And we see now what the effect of this minus I epsilon is. Namely, the minus I epsilon means that it's the Green's function that actually is the mean value in the vacuum of the time-ordered product of two scalar fields. Whereas if we didn't have the I epsilon, we wouldn't have had these particular poles. If we had the opposite sign for I epsilon, we would have gotten a pole here and a pole there, and things would have been probably, I mean, I don't know, I can't do it in my head, but it might have been that there'd be a minus sign here and a minus sign there. I'm not sure. But it would have been, we would have gotten something different. So that's the reason for the minus I epsilon. It gives you a Green's function that for this operator, and this of course is the operator, this is the Klein-Gordon operator for a field of mass M, a free field of mass M.
So why don't they call it the Klein-Gordon propagator?
Huh?
So why don't they call it the Klein-Gordon propagator?
Well, because when Klein and Gordon were working, they were dealing with, they didn't know how to do perturbation theory in this Lorentz invariant way that Feynman invented. They were using the clunky formalism of time-dependent perturbation theory in quantum mechanics.
But sorry, how did... Sorry, so in this delta plus of y minus x, if we flip the sign there, we change the plus to a minus. Like if we change, if instead of y minus x, we make it depend on x minus y, that changes the, yeah, that guy. I'm just comparing it to the expression that we have for the, oh god, I don't even know when I have it on my paper. Oh no. Sorry. Yeah, no, so sorry. Okay, so delta plus of minus x is delta minus of x, right?
Delta plus of minus x
is delta minus of x.
Did I don't think I introduced delta minus, did I?
Oh, well, I must be wrong. I thought, yeah.
I mean, the might, look. I mean, there are many notations. Somebody probably has introduced a delta minus, and whether it is what you said, I don't know, probably.
Okay.
Okay, well, so let's go back then to what we were doing. We were talking about a simple field theory, which is minus a half dA phi minus a half m squared phi squared, and then minus g over 3 factorial phi cubed. We were doing that theory, right? And we were talking about the scattering of incoming bosons of momentum p and k. Now, I don't quite remember when I jumped to do the propagator in this, but maybe since we've already had, we've just come back from fall break, so it might be useful to just say how this works. So one thing that can happen is that at this vertex, the P prime is emitted, K prime is emitted there, and then a boson goes across. Another possibility is that at this vertex, P and K are absorbed, and then something goes across and we have P prime and K prime. And then another possibility is just this, but now it's K prime and P prime. So that's basically the way people who've had some experience with theories like this do this calculation. So the amplitude for scattering then is P prime K prime minus 1 over 2 factorial, its second order, V of t prime, pk, and then, oh wow, there's a big typo. So this is times dt prime, and if you remember that V of t is g over 3 factorial integral phi cubed d cubed x, this turns out to be minus g squared over 2 factorial, 3 factorial squared, p prime, k prime, integral time ordered product, phi cubed of x, phi cubed of y, d fourth x, d fourth y, pk. So that's the amplitude that you have to compute. And now notice that we can think of this vertex as x and this vertex as y. And we have 3 fields available at each vertex, but of course we could equally well have had y occur, this be y, and that be x, this be y, and that be x, this be y, and that be x, and that's where the 2 factorial goes away. So if we just do these diagrams and forget about diagrams like y, x, pk, then we cancel the the 1/2, because it's 1/2 of the 6 diagrams is equal to the 3 diagrams. And of the 3 diagrams, the one that I analyzed first was the case where, it was actually this case where I think I had both particles absorbed at y. So actually, the one that I did was yx rather than xy. So let me rewrite it. yx, y, x. This is the way I actually then did it. And so then, if we have, let me just make sure. Right. Okay, so both particles are absorbed at vertex y, so 2 fields then, the annihilation operators from 2 fields do that annihilation. And so there are 3 choices for which field supplies the annihilation operator for A and P, and then there are two choices for which field supplies the annihilation operator for K, and similarly the three fields here creating the two final state particles, there are three choices for which one creates P prime, two choices for which one creates K prime. So altogether this is minus G squared vacuum integral time ordered product phi of x, phi of y, and d fourth x, d fourth y vacuum, and then the overall factors here are what? Well, each field kicks out a 1 over square root of 2 pi cubed twice the energy, and so we have 2 pi cubed to 3 halves, but 4 times, so it's 2 pi to the 6th, and then we have a square root of all of the energy, so 2p0, 2k0, 2p prime 0, and 2k prime 0. And then it leaves phase factors, and the phase factors are, for the annihilation operators, it's e to the I y, and it will be p plus k, e to the minus I x, p prime plus k prime. Is that more or less clear? And now what we've got left, you see, is the mean value in the vacuum of the time-ordered product, but that's the Feynman propagator. And so A1 then is minus G squared over this 2 pi to the 6th square root of, I'll just write product twice the energy. So it's the product of all the initial and final state particles. This is something that always occurs, or almost always. I mean, there might be exceptions, but it's essentially always occurring. What's left then is e to the I y p plus k minus I x. Oh, these are primes. No, this is right. P prime plus k prime. And then e to the I q x minus y. So what is the formula for the Feynman propagator? It's going to be minus I delta f of x. And so that's minus I, this integral d fourth q over q to the fourth, this denominator, and instead of x, x minus y. So this is e to the I q, x minus y, 2 pi to the fourth, q squared plus m squared minus I epsilon. The minus I epsilon doesn't really matter in diagrams that are this simple. These are said to be tree-level diagrams because if you look at it, you can imagine that these things are all trees. You can turn this on it, or if you just look at this one, it looks as though it has 2 roots and then 2 trunks. So it's, or 2 branches or something. So it's, and then you turn these guys on their sides and they become trees. Okay, and then there's a d fourth q. And of course we still have d fourth x, d fourth y. And left out one more thing. This time-ordered product is actually minus I times this. And so there's a minus I here. So it's altogether plus I, if we get rid of this term. So that's the formula, and that's equation 63 in the notes for chapter 6. Now, when you first see some crazy 12-dimensional integral like that, you might be frightened, but in fact Dirac comes to the rescue, because the d4th x and d4th y integrations only involve variables in the exponential, so that gives you two delta functions. And so that means that A1 is equal to IG squared integral d4th q over 2 pi to the 10th. Well, actually, no. The integral d4th q d4th x of the phase factor gives you 2 pi to the 4th times the delta function. So we're all the way down to 2 pi squared. Square root of the product of twice the energies. And then we get delta fourth of, let's just look at the x part. What's multiplies x? X is p prime, or minus p prime, minus k prime, plus q. So this is q minus p prime minus k prime. And the other one is the y integration, and it's minus q plus p plus k. And so that's what we have, q squared plus m squared minus I epsilon. And now you can see what that does. That says that q, when you integrate d4th q, that just sets q equal to p plus k. And so this is IG squared delta fourth of p plus k minus p prime minus k prime. This is the energy momentum conserving delta function. You then have 2 pi squared, square root of the product of all the e's, and then 1 over p plus k squared plus m squared. And it turns out now that since p and k are physical momenta, by the way, in something like an abuse, I think it's an abuse of language, instead of calling momenta that are physical, which makes sense, they're said to be on the mass shell. So we've taken one adjective that makes sense and turned it into on the mass shell. 4 words that are obscure. That's bad language. It's common in science. It's bad in physics. It's worse in astronomy. Okay, so that's what this particular amplitude is. Now, what about A2? Well, so which one did we do here? We did this one, A1. So let's call this one A2. So this is P goes to P prime, and what is the, I can just tell you what the answer is without looking at the notes. It's just 1 over P minus P prime plus m squared, and the other one is 1 over P minus K prime plus m squared. And let's just see why this would be true. You see here, you have p coming in, p prime going out. Energy and momentum is conserved at each vertex. That's this delta function here. The q is the momentum going, in other words, this q, you see, d4th q, this is the momentum going across here. And we see that one of the delta functions forced q to be p plus k. And so the way you look at this is you have momentum p going in, k going in, that's producing p plus k on this line. Here you have p going in, p prime going out, so this is p minus p prime. And over here it's p minus k prime. That's why you know that these are the other two terms.
So this is the full A.
Huh?
This is the full A.
Yeah.
This is the about 3A.
Yeah. Yeah. In fact, why don't I make this the homework problem for not Thursday, but a week from Thursday? So in other words, derive, I think deriving both of them, yeah, all right, derive both of them. Derive these last two terms by going through the same argument that I did in class. All right, so we're done then with this toy theory that illustrates basically the main features of Feynman diagrams are what we went through here. However, as you may have noticed, all the particles we know about are either fermions or gauge bosons, apart from the Higgs, or at least all that have been discovered so far. So we need to consider a process in which, when we go through a Feynman diagram, what we're left with is two fermion fields. And in particular, the case that is examined, the case that actually occurs is this. It's going to be the time-ordered product of psi L of x with psi dagger m of y in the vacuum. So that's what I want to do now, and this will be the Feynman propagator for spin 1/2. And, well, this is very much like what we went through. In other words, we're going to repeat the tricks. We're going to repeat all of these tricks, but there's one extra trick for fermions. And the extra trick is that in the definition, there's an extra minus sign. This is just in the definition of the time-ordered product. That's that mysterious minus sign that Weinberg says he'll tell you about later. Okay, so the definition of this is theta of x0 minus y0 psi L of x psi dagger m of y. In fact, the way I did it in the notes was I said, well, let's look at this in the most general way. Let's just go to spin 1/2 exactly. Then what occurs here is minus theta y0 minus x0 psi dagger m of y psi L of x. So there's an extra minus sign here. That's the extra minus sign. Now, why do we put in the extra minus sign? Well, the thing would be really psi suppose you imagine that x0 is equal to y0, then the theta would be, you can imagine that theta 0 is a half, because it's halfway between 0 and 1. So with the minus sign, what you have is psi of x, psi dagger of y, minus psi dagger y, psi of x. This is equal times. And these are different space points. So I'm just going to put in the space part. So this is with the minus sign. Without the minus sign, we'd get a plus. Okay? But that's 0. So you don't want the thing to vanish at equal times. That's why you put in the minus sign. So it's, I mean, that's how you know you need the minus sign. What else is the reason why there's a minus sign? Well, if you put in the minus sign and you do the calculation, you get the right experimental results. Or you get something you could derive some other way. Anyway, that's why you have the minus sign. Now, if we go through the same tricks as over there, what we see is this is psi plus here, and it's psi dagger minus, and here is psi dagger plus and psi minus. And then, if we turn them about, we get 0, so we can put in an anti-commutator here. We can convert this to an anti-commutator without changing anything. Once it's an anti-commutator, this is just a C number in the vacuum state, just sails through and gives you unity. And so what we get is simply theta x0 minus y0, anti-commutator psi plus L of x, psi plus L x, psi dagger, we need a different symbol than dagger because dagger and plus get mixed up. I wish someone had invented one and made it common usage, but no such luck. Anyway, theta y0 minus x, at least that I know of, maybe you guys know, but anyway, anti-commutator psi dagger plus of y m psi minus L x plus. Okay. L and M run from 1 to 4. These are the Dirac indices. Okay, well, what we do now, of course, is we introduce the recall that psi L plus of x is equal to the sum over S integral dqp over 2 pi to the 3/2. So that's dqp ul of p and s e to the I dx 4 vector a of p and s. And let's psi minus L of x. Well, it's the same thing, except this will be VL of P and S, e to the minus I P dot x, B dagger of P and S. And then, if you have psi dagger and ask for its plus part, what would that be? Well, psi dagger plus would be sum S integral dqp 2 pi 3/2, it would be the adjoint of this. So that would be VL star of P and S e to the I Px B of P and S. And psi dagger minus of x would be the same thing, but it would be UL star of P and S e to the minus I P dot x A dagger of P and S. So those are the four forms that we need. And now you remember that a couple of weeks ago we tortured ourselves working out the spin sums for spinners. And you may have wondered, you may have thought that I was, I don't know, bipolar or obsessive or something, that we went through that. But the reason is that we actually need it in order to compute the Feynman propagator. So remember, what we computed there was that there was a matrix, and the matrix elements are L and M. This is the spin sum UL of P and S, U star M of P and S, and we computed that to be minus I of PC gamma C plus M times beta. Remember, beta is this 0, 1, 1, 0 over 2p0, and it's this thing, Lm. The other one is called M of P, Lm, and that's sum on S, VL of P and S, V star M of P and S, and this is almost the same thing, except for a minus sign on the M, beta Lm over 2p0. Okay, so we're basically done. All you have to do is compute this anti-commutator and that anti-commutator using these expansions and these spin sums, and then you get an expression for the Feynman propagator for spin 1/2. So that's in the online notes, but I think we have time to do it in class. I think I'll start out on the whiteboard while the whiteboard dries, and then go to the blackboard if we need to. So the tone of my voice may have given you the impression that there was no need to ask questions, but remember, I still have plenty of candy if you ask, if you have a question. Okay, so no questions yet. All right, so I'm liable to run over your well, maybe not. let's see what we've got here. Okay, so if we put these things together, what do we get? What we get is 0 time-ordered product psi L of x, psi dagger m y. Boy, this pen that I've only used once or twice is, oh no, there it is, okay. And so what is this? This is theta of x0 minus y0. And what do we have? Well, we have this anti-commutator using the fields. So let's see, okay, to figure out what to put in there, let me do these anti-commutators first. So the first term is psi plus L of x with psi dagger minus of y m anti-commutator. And this is then the anti-commutator of sum on S integral dqp 2 pi to the 3 halves UL of P and S e to the I px. That's, A of P and S. And if I put in the anti-commutator quickly like this, this will be a dagger of K and R. Instead of S, I'm using R. And now the rest of this is sum on R integral, what did I say, K, d cubed K, and now it's just 2 pi cubed. And e to the minus I k dot y, and now it will be u star m of k and r. Sam, you don't seem happy.
What? No, it's raining outside.
It's what? It's raining?
Yeah, it's like it's raining right now.
Good God. I thought this was New Mexico.
That's good.
All right, so we don't need this overall bracket because I've just put the bracket on the business part of the expression. This, of course, gives you a Kronecker delta and a three-dimensional delta function. And so this is, in effect, a spin sum. It's an integral d cubed p, 2 pi cubed, sum on S, UL of P and S, U star M of P and S, and it's e to the I P x minus 1. But now, this is the spin sum that I wrote down over there, and so this is actually integral d cubed p 2 pi cubed minus I. Now this notation, PC gamma c, gets tiresome. Feynman introduced the notation p slash for that.
Yeah, just to recap, why was it again that psi plus dagger is not actually what you get whenever you take the adjoint of psi plus?
Say that again now?
Psi plus dagger is not actually...
Psi plus...
That's the
No, it's not psi plus dagger. It's psi plus and minus and psi dagger plus and minus. So
Okay.
psi... Psi dagger plus is not the same as psi plus dagger.
Okay. Okay.
That's a great question,
Okay.
though.
Yeah, I see.
That's one of the subtleties here.
Yeah.
So you've kind of pointed it out for everybody. So this is minus I p slash plus m over 2p0 lm e to the I p x minus y. And then the other one, the other term that we need is psi m dagger plus of y anti-commutated with psi l minus of x. And that, well, it's the same thing basically. Sum SR integral dqp dqk 2 pi cubed, and it's just V's. So VL of K and R, VM K, well, actually I should say P and S. P and S, K and R, star, and it's e to the I P Y minus I K X. And it's the anti-commutator of B of P and S, B dagger of K and R. And that, of course, knocks us down to a delta function. So that's integral dqp 2 pi cubed spin sum VL PS VM star PS e to the IP y minus x. Well, that's it, y minus x. And then this spin sum is then dqp, it's what I wrote on the board over there, 2 pi cubed minus I p slash minus m beta over 2p0 lm e to the IP y minus x. Okay. So now we have the two things that have to go into the expression for the Feynman propagator. Do you guys prefer the whiteboard or the blackboard? Because it's dry now.
Blackboard.
Blackboard's good.
Blackboard? All right. Okay, so let me move this to the side. All right, so here's what we have then. As I say, this is in the notes, so you don't really need to copy this down. Psi L X, psi dagger M, Y, vacuum equals theta x0 minus y0, dqp pi cubed minus I p slash plus m beta 2p0 lm e to the I p x minus y and then minus theta y0 minus x0. This is that built-in minus sign, integral dqp 2 pi cubed minus I p slash minus m beta 2p0 lm e to the ip 1 minus x. Now, of course, minus I p slash e to the I px is the same thing as minus d slash e to the I px, because the derivatives bring down ip, and so you get minus ip slash. And so what we can do here is we can write this as theta x0 minus y0 minus d slash plus m beta lm on what's left here, dqp 2 pi cubed, this space factor. That is delta plus. And then we have minus theta y0 minus x0. This thing we pull out as d slash minus m, d slash minus m beta lm 2p0. Oh, I'm sorry. The 2p0 is inside. So this acts on this and pulls down this structure over. So what we have is this is outside, and the thing that's left is delta plus of y minus x. Now I skipped a step there. Is it clear what I'm doing? Or do you want me to stick the step back in? You want me to stick it back in?
Sure.
Okay. All right. Sorry. All right. So putting it back in, we have theta of x0 minus y0 minus d slash plus m beta lm acting on integral dqp 2 pi cubed e to the I p x minus y over 2p0. So this gives you that. And so 2p0s are here. These are the phase factors. The derivatives bring down p's. Then the next term is minus theta of y0 minus x0. And if you want me to write this explicitly, it's dA gamma A minus m beta lm, and what's left is dqp 2 pi cubed e to the ip y minus x 2p0. So these derivatives bring down minus ip. On the other hand, this integral is delta plus of x minus y, this integral is delta plus of y minus x. Now, there's one more trick and we're done. The trick is if we multiply this minus sign through here, we can put a plus here, minus there, and a plus there. So now we've got the same differential operator on both structures. Suppose we pull the differential operator out and write this as minus d slash plus m beta acting on everything to the right. Well, what we would have would be theta of x0 minus y0 delta plus of x minus y plus theta y0 minus x0 delta plus of y minus x. Except for one thing. So so I'm going, remember the order here is this one to this one to that one to this one. So it's A, C, B, D. Now, the problem is the time derivatives. When the time derivative hits the step function, you get a delta function. So we have to compensate for that delta function. The compensation is that this is minus d0 gamma 0. So when minus d0 hits this, we get minus delta function. So we have to add in plus gamma 0 delta x0 minus y0 gamma 0 times beta delta plus of x minus y. But then when this minus d0 hits minus that, we get plus delta, so we have to subtract this one. So we subtract gamma 0 beta delta x0 minus y0 delta plus of y minus x. Okay, so these are the things that compensate for the delta function. But now we see that's just the same. We have a common factor. So factoring out the common factor, what we have is this, delta plus minus delta minus. But it's to be evaluated at equal times. At equal times, delta plus of x is equal to delta plus of minus x for x0 equal to 0. So if the times are equal, this is that. So in other words, the ugly term is 0. So what we're left with then is this very nice structure here, minus d slash plus m beta Lm acting on this. But this thing is the Feynman delta, is delta F. And so this is not the final expression, but we're over time. So let me just write out where we can start next time, which is almost the end. This is then minus dc gamma c plus m beta Lm acting on minus I delta F of x minus y. Or equivalently, it's this structure here acting on d4th q 2 pi to the 4th minus I over q squared plus m squared minus I epsilon e to the I q dot x. Okay, so that's the answer. There are various ways we can massage this, and we can talk about that on Thursday. Any questions?
Okay.
What's that?
Okay.
Sure.